I will be the session coordinator. Myself, Vishwateja, research scholar from IIT Bombay. We are here at West 1. The topics. I would like to introduce the chair and co-chair for this session. Our chair for this session would be Dr. S. Hemant Chore, Associate Professor from NIT Jalandhar. He is in the academics and research development since 1994. He has guided around 10 PhDs and more than 55 ME MTechs. He has got more than 75 journal publications in indexed and peer-reviewed journals. He has got more than 225 publications in conference proceedings, etc. We welcome you, sir. And our co-chair for today's session, Professor Pino Mering, Assistant Professor, Geotechnical Engineering, IIT Bombay. She's completed her PhD from IISc Bangalore. Her research areas are land size, probabilistic methods, risk and reliability analysis, mesh tree techniques, material point method, large deformation problems, etc. We welcome you, ma'am. Now I request our chair for the session to please introduce our thematic lecture presenter and start the session. Thank you.
Good afternoon, everybody. Welcome to this particular session wherein the paper selected the theme of the slope stability and landslides will be presented. So today we'll have a thematic lecture on integrating TabNet and SHAP for interpretable landslide susceptibility modeling in Minnesota. The theme speaker is Surya Sharat Chandra Congress. And in addition to this, there will be around 4 contributed presentations related to the various aspects pertaining to the theme of this particular session. So, now I welcome Dr. Surya Sharat Chandra Congress and will introduce in brief. He has completed his PhD from University of Texas. He is currently working as the assistant professor, tenure system, Michigan State University. He delivered several invited lectures on national and international platforms, including Transportation Research Board, Unmanned Aerial Vehicle Commercial Expo, DJI Airworks, and the International Society for Soil Mechanics and Geotechnical Engineering's Bright Spark keynote lecture at Cairo, Egypt. He is also a member of 2 National Academies Transportation Research Board committees and also served as a TRB Committee Communications Coordinator for one of those committees. He is a part of the ASC Committee on Innovative Technologies and Tools in Geotechnical Engineering Task Force. With this brief introduction of Dr. Surya Sharat Chandra Congress, I invite him for his theme lecture. Thank you.
Good evening, everyone. I hope I'm audible. So, today I'm going to present our research on using TabNet, a type of deep neural network, as well as SHAP, an interpretable approach to understand the landslide susceptibility of Minnesota. So, I think it should pick up. Hopefully, I try to walk around. So this is the presentation outline. I will be briefly going over the introduction and landslide susceptibility mapping, as well as some of the study objectives, and then discuss the methodology. And we'll also talk about the results and field validation using drones, and then we'll conclude. Since we only have 15 minutes, and I also have a presentation in 30 minutes, I'll try to make it brief, but if you have any questions, feel free to reach out or ask me at the end of the presentation. So with that, let me go over briefly. Slope instability is a widespread geological hazard, often manifested as landslides when large soil or rock masses fail. Why do they fail? There are a lot of triggering factors, and common ones are rainfall or seismic activity, which cause the shear stress to exceed than the material shear strength. Then failure happens. So these events can be catastrophic, especially causing damage to infrastructure and life. And you can see we'll be focusing our discussion on Minnesota, USA, and this is the landslide that has happened in 2014. So in regions like Minnesota, landslides have historically led to considerable economic losses. Why? Because maybe in India, we might not face it too much of, especially most part of India, we don't face the freezing and thawing, but in Minnesota, the temperatures can go up to minus 40. When I say minus 40, I'm not even talking about whether it is Celsius or Fahrenheit, because it doesn't matter. It's the same, minus 40. So with that introduction, let me go over. They spend millions of dollars annually to repair. So when you have only finite amount of resources, you might want to prioritize high risk areas that you can make informed decisions. So for that, we need to do landslide susceptibility modeling so that we can understand the likelihood of landslide happening. For example, imagine there is a road network. So if you know which parts of the road network are exposed to this landslide, we can prioritize which areas can be addressed and rehabilitated soon. So typically, past studies have integrated GIS and statistical models to conduct this landslide susceptibility mapping. So I won't be going over different types, but I'll be directly jumping into the models that we used, which is, as you can see in the objectives, we are using a TabNet. So I'll go over the architecture of the TabNet briefly as well when I move on to the next slide. But the idea is to create a landslide susceptibility map for Minnesota using TabNet. And then once we have the model, we want to develop a high resolution map of Minnesota so that the departments of transportation agencies can actually see which ones are the critical zones and make informed decisions, and also validate. Because if you are only going to model and not validate, validation is when you do modeling, we always do validation within the model. But what I'm talking about validation is use field investigation methods to validate it. So that's what I'll be augmenting in my slide. And I'm sorry. So we are also going to briefly touch base on the explainable AI part, because how many of you think machine learning is black box? You don't know what is happening inside unless you have certain techniques called explainable AI to understand the influence of the causative factors. Again, this is just a brief study that I am presenting, but we compared multiple methods and which is under review. I'll be happy to share any of those results once it is published, but feel free to ask me if you have any questions at the end. So this is the you can see the American map here, and this is the Minnesota map. So these are just information regarding Minnesota. But one thing I want to highlight is this Minnesota map or Minnesota area has wide variety of soils. For example, this area has a lot of high PI clays. So when I say high PI clays, which mineral comes into your mind? Montmorillonite, right? So when you have Montmorillonite, what happens is the soil will expand. So like Dr. Pupa always says, they are not expansive soils, they are expensive soils because they result into lot of repairs. And so we are going to talk more about the areas in this red zone here. So the methodology is, first we collected 7,000 landslide points from various resources, and you can see those plotted here, the red ones. And then once we have 7,000 landslide points, we also created non-landslide points equally, and we used both of them together to model. So when we used 14,000 points, we split it into 70% and 30% for training as well as validation. And we'll be talking more about the results shortly. But before that, what are the causative factors? Basically, the well-known causative factors in the literature were adopted. As you can see, these are the 10. And once that is, we selected them, the first step is to see if they are interdependent. Because we don't want to use dependent variables. So what we did was, we did multicollinearity analysis. Again, this is one of the methods that were quoted in the literature, but there are also much more advanced ones. But I'll just briefly go over. We did the degree of multicollinearity for all the variables involved. So we calculated VIF using this formula, and based on the literature, if VIF is less than 10, then it indicates independence. So which is what we want to do before we perform the modeling. So this is the architecture that we use. How many of you are familiar with deep neural network? Okay, great. So we have a lot. So others, okay. I understand that you might be familiar with it. So I'll help facilitate you understand what is deep neural network. So basically, let me ask you, how many of you know? Okay, great. So you know orange, right? Very good. So how do you know an orange is an orange? Sorry to put you on the spot.
No, my mama told me orange.
Very good. Perfect answer. Perfect. So, parents or teachers are taught us, right? So now, can we apply the same thing? Me being the parent, teach the computer to do it? So that is what exactly we are doing with deep neural network. So we are simulating the neurons in the brain structure in learning process and training the computer to do, okay, hey, this is an orange. So next time in the future when you see an orange, tell me it is an orange. So that's the basic idea of deep neural network. So now, let me ask you, how many of you are familiar with deep neural network? Same? Or someone? So, if you are not familiar, please feel free to, reach out. I'll be happy to provide more details. But in this study, we are going to use TabNet, which is a tailored deep neural network for tabular data. And this is the core architecture of the TabNet. Again, like I said, I'm not going to go over in detail, but I would like to highlight two building blocks, which is one is feature transformer and the other one is attention transformer. So feature transformer helps in learning the representation. So basically we feed in the data, right? So when we feed in the data, this feature transformer will learn the new representation of the input features and then outputs some information which will be transferred to attention layer where it actually identifies the most relevant things to be trained upon. So again, I don't want to explain all the architecture, but just give you an idea, how does it work? Imagine a room full of, let's say, minerals, but it's dark. So now, if you want to see which minerals are there, you use a torchlight. So when you are using a torchlight and doing this process, the way that we are using the torchlight and also processing, that is what these two layers does. So basically it's a sequencing problem where we do it multiple times continuously. So with that introduction, I'm going to say we validate. So basically when we train, we fine tune the hyperparameters until the validation accuracy. How much percentage of validation data are we using? If you remember from the starting?
30.
Very good. 30%. So 30%, we use that to arrive at these hyperparameters, and these are the values that we obtain. Again, you need to fine tune it to get the maximum accuracy on the validation data. So, and then these are the multicollinearity results. So as you can see, VIF is somewhere here, and if you see, they are less than, all of them are less than 10, which means most of them that we captured are not dependent. Again, we are also adding one more additional parameter to evaluate the multicollinearity, but this is something that we have done recently, so I just wanted to highlight here that none of them are statistically dependent. So that's what we identified, and these are the results. How many of you are familiar with true positives, false negatives, just from the name of it? So if you see, these are the true labels, basically landslide and non-landslide, and these are the predicted labels. So if a predicted label is same as the true label, then it is called true positive, TP. That is what is important for us. And if the non-landslide, which is true label, is this, and predicted is also this, that is true negative. So these are the most important ones, and the rest, for several models, especially in geotech, this is a good number for us. As you know, there is so much variability happening, right? And we also calculated the different performance. The reason I'm not going to go over here or these results in detail is most models, when we do modeling, we will get good results or we'll try to fine tune, right? But the next part that I want to highlight here is we are going to use validation in the field data. But before that, let me see. So this is the so if you see, that's the landscape susceptibility map that we developed from TabNet, and we see there are different classes, very low to very high, and these are the percentages. So I'm going to pick a couple of random spots. Which one is, oh, this is SHAP. Again, I'm not going to go in depth in this, but SHAP is like Shapley additive information. How many of you are coming to the gala dinner in casinos tonight? No? Okay. So basically, SHAP is based upon the same gaming theory, where you add a component and see how it is changing the output. So that's how we try to develop a SHAP explanation for this modeling. And I'm going to briefly go over this first one here, and then, if you have any questions, I can talk about it. So first one is, these are the cause-weighted factors, right? So if you see, this is low and high. What color do we have here? Is it low or high for slope? Very good, low. And now, if you see, if the slope is lower, then the impact, which is landslide, basically, is reducing. But if the slope is higher, if you see, then it is increasing. So basically, you understand, for each causative factor, this color will give us an idea about how it is impacting the output of it. Okay? So that is the explanation part. Again, this is very helpful. Why? Back in the day, machine learning models are mostly black box. But here we are giving an additional explanation to understand the results. But now we will move on to two sites, as you can see, Climax and Minneapolis. How many of you have been to 2022 Geo Congress in the US before the COVID shut everything? Okay. So Minneapolis is where it was held. So let's see. So this is the Climax site. Remember when we looked at it in the previous one, it is having somewhere close to medium to high, and the same thing as well, it's close to low. But let me show you certain spots. Again, if I zoom in, we noticed these sites have higher landslide susceptibility, and this is an independent TV reporter which showed 25 feet drop of a cornfield, as you can see from here to here. So this is from the TV network, but what I'll show next is, this is historical imagery. How many of you have used Google Earth to go back in time? So that's the same thing that we did, August 2015, and I would like to highlight here, there is no distress, but what we see in September 2022, this again is clayey soil, high PI clayey. So if you see a crack like this, it is tension crack. So this is how it looks in April 2025. As you can see, it is increasing. Why? Because of freezing and thawing, the soil will further desiccate as well and create these cracks here. So what is happening because of this? The soil is failing, and this bridge here, there is a bridge. You can see this river. So it is actually moving as well. So that is one reason we got a project with Minnesota Department of Transportation, and we were working on it for the slope stability using geotechnical approach as well. But this one is an overall approach that we conducted, and let me show you. This is the Climax site. And how many of you have flown a drone before? You did? Did you successfully land? Because flying is one thing, but landing is also another. Did you? Okay, good. You're a better pilot than me then. So this video that you're seeing is an animation of a 3D model captured using drones. What do you see here? The same one. That's the same crack, and at a higher resolution than Google Maps. So I provided the animation here, but what we are trying to do as part of the project is we are using the superficial geometry with soil parameters to do a thorough 3D slope stability analysis. How many of you are doing 3D slope stability analysis? Okay. How many of you are did 2D slope stability because that is more common, right? So we are moving to 3D slope stability analysis because this is a very complicated site and we want to consider both end effects as well as the variation. So we are doing probabilistic stability analysis, which maybe hopefully in the next IGC I'll be able to present. But what I'm saying is, you see the bridge here, right? So this is the ice there, and this is the normal time. As you can see, in summer there is still this distress. There is around, the drop is around 1 meter here. As you can see, the cornfield was 25 feet, and here it is 1 meter. And what is happening on the bridge? This pier, because the soil is moving, the base of the pier is tipping this side. So it is causing the distress on the bridge. So now, for the slope stability analysis, we use bare earth. So basically we cannot consider the vegetation and all, right? So these are the points that we are using to generate bare earth surfaces to conduct the slope stability analysis. So I just wanted to give you an idea that yes, we also validated it for our modeling, but now what do? We are expanding it to conduct detailed slope stability analysis so that we can understand why it is failing and create the active movement zone. Because even on the other side, especially here, there is a tension crack that has happened throughout. But it wasn't clear why, because it belongs to a railway agency and the DOT couldn't access it and they couldn't even know until we used the drone. So basically drones, you can fly and capture the data remotely. So with that, I'm going to move on to the next final site. So as you can see, this is Minneapolis site, which is probably a mile away from Minneapolis airport. And you can see this is the road, highway. And you can see this drop, 100 feet. 100 feet drop. And in 2012, a couple of kids also died because of this landslide. And also another thing is, this lady here, let me show you this video. So if you see, I was actually flying the drone. Is it playing? Okay, now it's playing. So if you see this home here, so I talked with that lady and they have been in that home for like 40 years. I asked them, hey, this is sliding, right? She said it moved at least 50 feet inwards and the slide has happened. So they are still waiting because if it moves further than 5 to 10 feet, they need to evacuate. So I asked, why did you guys stay? They said the views are worth it. I mean, from the view, they can actually see the Mississippi River and all. So they mentioned it's worth it. But as a geotechnical engineer, we want to understand this stability. Why? Because you can see the highway is just close by, probably 30 to 40 feet. And you don't want, especially when there is a rainfall event happening, you don't want cars applying even more load, right? So that is what we did. Again, we are trying to validate our landslide mapping, but I'm also combining it with other project where we're also doing 3D slope stability analysis to understand the stability or critical zones. So I'd like to conclude, we demonstrated the applications of remote sensing as well as deep neural networks for landslide susceptibility mapping. And again, we got the accuracy of 96%. I'm not concerned about it because when we are doing modeling and if I'm presenting the results, we'll only get best or provide best results. But what I want to highlight is validating it with the field data or adding the explanation using SHAP. Those are the things I would like to highlight here. Why? Because it will help the agencies in making informed decisions for sustainable infrastructure. So with that, I'll be happy to take any of your questions in the next 5 to 10 minutes so that I can start running. Yes.
Sorry, I have many questions, but I will ask you questions.
Okay, thank you.
The first thing is like, you didn't mention how you generate the non-landslide points.
Okay, that's a good point. I did mention we collected it from different agencies, so we did not generate them, we collected them.
No, landslide points is like you use the polygon first, or point.
So the location coordinates of those landslide points are available from USGS and different agencies. Again, I did not include it because of the time.
I got it. Like you just have a point data.
Yes.
Not a polygon.
No, point.
The point is like which part of the landslide?
The centroid. Because we have polygons and we generated the centroid because that is one meaningful way to select those points.
As a geotechnical engineer, we need to focus on the failure point.
Okay.
That is one one suggestion. And then how you generate the known landslide point. That is very interesting when you are doing machine learning kind of things.
How
You didn't mention how you generate the known landslide points.
known or non?
Known.
Okay, non. Okay, thank you.
Zero for the model.
Yeah. So what we did was we created a buffer zone around the landslide points and then started creating multiple non-landslide, because when the landslide points are known, we're using that to create the non-landslide.
Buffer distance.
500 meters.
And then your accuracy is very high. I'm not happy with this kind of accuracy. If you are really did good, if you want to make a good model, then if 90% and above, I reject that model because this is just bias. And then did you check any special biasness of your model or not?
So a couple of biasness can be due to the data that was collected by USGS, and also they might not have captured all the failure zones, right? So that's something we'll be happy to add more and more data. But my study, I'm not trying to boast that 90% is my best thing, but my pitch here is use explainable AI and also complement it with field data. That is my pitch. Again, I did not specify 96 is great, give me a trophy. No. Because, see, when we obviously try to model, we try to get the best ones, right? So, and also we did the multicollinearity analysis. I'm adding additional parameter to check linearity as well. So probably we might be able to get interdependency between those 10 causative factors as well. So that is something that we'll be doing in the future as well. But the explainable AI is something that we as geotechnical engineers haven't used. That is my pitch.
Yeah, but I didn't see the rainfall.
I'm sorry?
Rainfall.
There is.
Covariance is a rainfall.
TAR or something. Yes, rainfall was there.
Rainfall was there?
Yes.
But the categorical variable, how you did how you fit to the machine. Suppose soil and then some LULC are there, but how you make an input for that?
Good question. So basically for LULC, we have vegetated and different types, right? So we assign a class and then the class number is inputted. Basically when we collected the data from the online sources as well, they've assigned a class. So we used that class to define, okay, from this area to this area, this is a class. So we assigned a class to give you the answer, okay? So, I mean, those are amazing questions. I'll be happy to provide you emails as well so that we can talk.
Yeah.
I would like to see if anyone else has any other questions as well. Before, again, like I said, I need to go to C2C or somewhere for my next presentation. So, yes, any questions? Thank you. What's your name?
Tulas.
Tulas. Thanks. Yeah, sure, absolutely. Any other questions? Okay. Thank you so much.
Thank you, Dr. Surya Chandra, for your nice presentation. With this now, I hand over the session to my co-chair.
Before we move forward, I request the chair and co-chair to please present a memento to our thematic lecture.
Thank you. Sorry, I had to leave.
In this session, we are going to have current presentations, and the time allotted has been extended, so it can be 10 minutes. Each presentation will be given 10 minutes of time. Okay? So then we shall start with the first presentation of the session, which is fragility of rock infrastructure. Slides in Uttarakhand, India, by Akshay Vashisth.
Hello, good evening everyone. So my name is Akshat Vashisht and the topic of my today's presentation is fragility of road infrastructure against landslides in Uttarakhand, India. So So this is the outline of my today's presentation: introduction, study area, data and methods, results, conclusion, followed by references. So what is fragility and why we used to need it? So here fragility refers to the ease which something breaks under the stress. So here what fragility means. So for transportation, if we finding the fragility, it will inform us about the how bridges and roads are reacting when they are just hit by the some natural hazards. It may be a flood, it may be an earthquake, or it may be a landslide. So from the fragility we can know about how it's like it's a completely damaged and or it's a partial damage or it's fully damaged. So with the help of this it will be help us to plan the how we can make the transportation network more stronger, and it will help us to planning for the emergency response during the some disasters happen. So and what is the need of the fragility for us? So mainly in the Himalaya region, when any natural hazard happens, if it will disrupt the transportation network, so the many of the remote villages, they will cut out from the mainstream, so they cannot able to get the proper health cares and emergency help from the government. And if like in hilly areas mostly there is no more alternate route, so if one route is closed, so they will get isolated from the other communities or other structures. So for us, fragility analysis is very useful. That will help us to find out how vulnerable are the transportation network and how can we find out the functionality loss on it, and it will help us to design a resilient design to reduce community losses. So this is one of the table. It is from the 5 years data, which showing that for how many days these four main highways, Kedarnath highway and Rudraprayag to this Kedarnath highway, Badrinath highway, Yamunotri and Gangotri highways are closed in these 5 to 6 years during the June, July, August and September months. So during 2013 event, so the highways is closed for more than 60 days. So we need to focus more, like during the rainy seasons, the highways are getting closed more. And these are the other global and national data which showing that due to the landslide happening in the different regions that disrupt the transportation network, and due to the disruption in the transportation network, the people are in very trouble sometimes, and because they are not getting the needed items, emergency response and other so this is my study area. So I am working on Uttarakhand regions, which is like spread across the greater Himalayas, lesser and Shivalik Himalayas. It's received 50 mm rainfall annually, and due to which it's the soil are saturated more and it reduces the shear strength, and we experience a frequently shallow landslide there, which has a depth of 5 to 10 meters. And why this area is important, because it's not important only because it's a religious highways, but it's also strategic for the our military purposes also, because the military also use these roads and it's very useful for them. So for this I use the road data from the NIDM report and PWD data, then I just digitize it using the RGS map on it. And for landslide I use the ISRO inventory from Martha et al 2015, which is taken from the list 4 imageries from the satellites. And for global fragility data I use the Rajan et al 24 paper. With the help of this I will derive the landslide area and landslide volume for finding the fragility curves. So what methods are used? Fragility estimations, landslide area and volume are used to find out the then classify the severity, then assign the damage factors to them to find out the fragility curves. So for finding the fragility of curves, we find the probability of road damage versus the landslide intensity, validated using a global data set. So in this, we combine the road infrastructure with the landslide, and with the help of that, we find out the fragility of these 4 highways in Uttarakhand. So for finding out the volume using the landslide area which is given in that inventory, so we use this formula from Zamir et al. So this is the formula we use for. In our case, in mostly Uttarakhand there are debris slides or rockfalls, but in our inventory the mostly are the debris slides, so we use the debris slides formula. And for calculating the damage factors with the help of landslide volume, landslide area, these formula is derived with the fitting curve from the data when it's overlaid with the road data and landslide data into the HarmMap. So in this study, the fully damage is considered like if the road is completely covered with the sediments from the landslides. So first, these are the results from fragility curve for Badrinath highway. So we can see that the damaging factor here is like going up to the 0.7. So it means 70% damage will be happen from the 4,000 m³ of the landslide volume. And here in the landslide area also, it's going up to the 60%. So we can say that because the Badrinath highway length width is around the 14 meter. So if the landslide volume is very high, then also like it will not completely block or abrupt the district transportation network here as we compare to the other highways. So these are some images from Badrinath highways which show that these are the continuous landslides and the landslide volume is more than 10⁴. Then also it's not like the transportation is still working. It's not like completely damaged, or we can say it's stopped due to the big landslide happening there. In Gangotri case, like the same amount of the landslide volume is happening, but still the damage factor, or like we can say the 80% of the road is blocked due to the debris sediments. In this, like we can say we know that the geology of the Gangotri is a Tertiary sedimentary zone. Still, it is weak in compared to the other, like Badrinath highways, the medi-sedimentary rocks, so and metamorphic rocks. So there's a weak in geology part of it, and the width of the road is in Badrinath is 14 meter, and here is 10 meter. So if the same volume of landslide is happening here, so it creating a more damage to the road as compared to the Badrinath highway. So these are some images which are from the Gangotri highway. Same in the Kedarnath area, the fragility curves when we depthing, so damage factor is coming around 60% to 70%. So in this area, like for up to some extent, it is like more resistant to the low volume landslide. It is not getting more damage as compared to the Gangotri one. These are some images of the.
Akshay, you have another two.
Yes. So these are the results from my last Yamunotri highway. In this, like we can see that the damage factor is going up to the 1, means like 100% damage is there in this highway. So in this highway we can see that the volume is like much more than the other highways. It's going up to the 5,000 m³. So due to this, and the width is about 7 meter of this highway, so it is getting the fully damaged. And this highway is very narrow, so if it's like 1,000 m³ landslide volume is also happening there, it also like partially damaged this road network. So these are some images, and these are the conclusion that according to the volume based analysis, it revealed that the Gangotri and Yamunotri highways are particularly vulnerable to the high magnitude debris flows with steep fragility curves. And if we compared with Badrinath and Kedarnath, they showed more gradual changes, but they have the high tolerance than these two highways. So these are some references. Thank you.
We can take 1 or 2 quick questions. Okay, anybody? So thank you, Akshay, for the presentation.
Thank you.
So, thank you, Akshat, for the presentation. Now, I would like to welcome the next presenter, Kalpana Adhikari. She'll be presenting on integrated geophysical and geotechnical assessment of unstable slope in Kaligandaki corridor, Nepal.
Good afternoon, everyone. It's an honor to be here in Geotech Asia. My name is Kalpana Adhikari, and I work for Department of Roads, Government of Nepal, as a senior divisional engineer. And my presentation is based on the studies that we carried out in our project. This is the outline of my presentation. I will be presenting the case studies of two landslides, Khambhita and Maldunga, the investigations we carried out and the protection measures that we proposed. This is Nepal. As we all know, it's a small country, but with an average width of around 200 kilometers, we have elevation differences from 51 meter to 8,848 meters, the highest peak in the world. So, in the past 20 years, the road construction has been increased significantly. And similarly, the landslide events and road closure location has also been increased, and the cost of damages is also increased drastically. In the in a week back, before we come to Geotech Asia, there was rainfall for 3 days, and the loss of the damage was. Was 12 billion. So this is the scenario in Nepal right now. You can see this is the road network of, this is the highway network of Nepal, and the green line shows the Kaligandaki corridor. It connects India and China. It is the shortest route through Nepal, connecting India and China so far. It is very important for Nepal because of 2 reasons. First, this serves as a trade route, so Nepal can get benefited from 2 large economic activities countries. And second, it serves as a tourism route, especially the Indian people travel through this corridor to visit Muktinath and other holy places, religious places. So this is very important road. It passes through very beautiful places. However, constructing road in this corridor is not that easy. It's very challenging because it passes through the major throats, geological throats of Himalayas. So this is the methodology that we followed. Generally, we followed the same methodology while assessing the landslide in Nepal. First, we collected some information, important information from desk study, and then we visited the site and geophysical investigation was done. Geotechnical parameters were observed, and then numerical modeling, and then the protective measures was proposed. So the first case is Khambhita landslide. When we visited Khambhita, we could see the large cracks at multiple locations at the slope. There were high CPS discharge at the road level. There wasn't any movement at the valley side. It was only at the hillside. So the major problem of the landslide was unmanaged surface runoff and some of the subsurface moisture as well. So another reason for failure, not only in this case, but everywhere in Nepal, in hill roads, is road construction is carried out in haphazard manner. Means without any adequate benching or other slope stabilization measures. As a result, failures frequently occur and mitigation measures are provided afterwards. So this is the profile of the slope obtained from ERT. And this is from geotechnical investigations. So this is the slope considering the slip failure at the first picture is the first analysis is considering the slope slip surface at the middle of the slope, and the second one is at the toe of the slope. In both the cases, the factor of safety is less than 1. Of course, that's why it is there we can see the failure. So after providing mitigation measures, now the factor of safety is almost 1.5. As I mentioned before, the main problem observed in the site was surface water, surface runoff. So we suggested surface drainage like chutes, structures, and some retaining structures like gabion, rock bolting, and bioengineering is also very popular in Nepal. So we suggested bioengineering. And for further future monitoring of the slide, we suggested to set up the inclinometers. The next case is Maldunga landslide. In this landslide, we could see both hillside and the valley side is moving. There we can see some sort of failures, rock outcrops are there, and the main cause of the failure is soft surface drainage. So this is the profile obtained from the ERT. This is in the valley side, and this is from the geotechnical parameters obtained from geotechnical study, and the slope is it is obtained from numerical modeling. The valley side, the left one is the hillside and the right one is the valley side. Here we have the factor of safety in hillside less than 1, and in valley side it's just about 1. So after putting the appropriate mitigation measure, we can see the factor of safety is 1.6 and almost 3 respectively. And as I mentioned, the main problem of the failure, the main cause of the failure is soft surface water. So we have suggested the soft surface drains, the perforated pipes, and geotextiles. And gabion is also very much applicable in the slope where we see the slope movement. Creeping is there. So again, bioengineering, geomembrane, and for future slope movement, inclinometer monitoring is suggested. So from these 2 cases of landslide in Kaligandaki corridor, we can see the general approach used for land assessment. This is the general approach of land assessment in Nepal. Since each landslide has its unique characteristics, every site must be studied individually and addressed with site-specific solutions. In these 2 cases also, as they are located very near, but the cause of failure are different, so the solution is also different. To conclude, in Nepal, we focus on implementing low-cost solutions as proposed on those 2 landslide cases, Khambita and Maldunga. Thank you so much.
Okay. Any questions? Okay. If not, I just have a question. So you did some ERT test, okay?
Yes.
Okay. So what did you find? What are the implications that you could obtain from the ERT test done?
We can find the groundwater table and the slip plains, probable slip plains. due to from the resistivity, we can find the types of soil parameters like loose soil or rock outcrop and something like that.
Okay, so how is it different from the other regular geotechnical investigations test? I mean, what value addition is it giving compared to the conventional
ERT
tests like
ERT
CPT
is
or
geo-
SPT? Yeah.
Okay, ERT is a geophysical test. So from the electrode that we put on the slope, we get the different resistivity, and we can, based on that, we can find out the types of the materials inside the slope. And we can verify through SPT as well. From SPT, we get the geotechnical parameters. We get the core, and and from the borehole also we get the geotechnical parameters, and we can compare those values.
So exactly my point. If somebody, I mean, usually we go for SPT and CPT. So in which conditions do you recommend the electrical resistivity test? Is there any specific conditions or sites where you would recommend those tests?
Now, ERT is, if it is possible, we recommend ERT and validate with the geotechnical test like SPT. Both are recommended to validate each other's data.
Okay. Thank you, Kalpana. Okay.
Thank you.
Right. So the next presentation is from Priyal Fernandez on lessons learned from the recent landslides in Goa.
Excuse me. Can I have it in presenter form on this laptop? Presenter form on this laptop. I have notes. Add it. Yeah, there's an option. When you when you present it, you get animation, slideshow, and presenter. You get an option here to press presenter. Okay. Good evening, everybody. Myself, Priyal Fernandez. I'm a research scholar at Goa College of Engineering, and here's my top. I'll be speaking on the recent lessons learned from recent landslides in Goa. Here's the overview of my presentation, starting with the introduction, the literature review, recent landslides in Goa. As of only landslides happened during the 2024 year. Then geology and geotechnical properties, observations and lesson learned, some mitigation measures, conclusions and references. Goa, the Pearl of the Orient, is situated between the Sahyadris and the Arabian Sea, and experiences a fairly heavy amount of rainfall, up to 3,500 mm annually, and enjoys a very tropical and a warm climate. Goa predominantly has lateritic soil with varying properties, and the color spectrum ranges from deep rusty red to yellowish white. The pictures shown are of different colored lateritic soil throughout Goa, and this lateritic soil can be very problematic in rainy season, leading to erosion, landslide, and other geohazards like settlements, cavities, etc. And over past years, Goa has witnessed many landslides ranging from infrastructural damages to loss of livelihood. Here's my literature review. In Goa, landslides have been happening often, especially during the wet season, and that have disrupted the roadways and have led to inconvenience to vehicles and locals. In the year 2024, there were 48 landslides recorded in Goa, Tiswadi Taluka being the most landslides, followed by Kepe and Marmugua Taluka. Major landslides with those happened close to the road highways and interstate routes, including the Malpe and Dargal, at the Pennem and Bicholim Highway. In the states of Goa, the slopes are being cut for numerous developmental reasons, and which has led to instability of slopes, which have not been monitored regularly and have eventually progressed and failed. These two significant landslides were also seen on the Vasco and Kortalim routes. The Cholla Ghat area of the Western Ghat range saw another substantial landslides, and the Western Ghat sees landslides every year. The reasons for landslides may be, one of the primary reasons of the slope failure is loss of shear strength in the soil mass, which might be brought by the lateral movement and underlying loss of support brought by the road cuttings and erosion, etc. Or it could be the reason of increased loading on the already unstable slope. This may be due to swelling of the clay, the hydraulic pressures, and lack of dewatering techniques. The water infiltration into the soil can also raise lateral pressures. The decrease in the material strength, which may be brought by the weathering and consistency changes, or an increase in the void ratio as a result of swelling and water along the shear failure planes, is another important factor when it comes to cause of landslides. These are the recent landslides that happened in the year 2024. This map was generated by our ME students during as their seminar part of the seminar. Sorry. And landslide depicts, the geology and geotechnical properties. Goa has a green schist supracrustal rock that lies on top of trondhjemite gneiss and what makes the most of Indian Precambrian shield. Under the influence of intense rainfall and high pressures, organic matter such as silica and lime leach to form lateritic soils. The lateritic soil is soft when wet and becomes hard when dry. The lateritic soil profile of Goa was studied by Widdowson in the year 2009. Consists of a top layer called the lateritic crust, which is red, heavy, and composed of oxides and hydroxides of iron and aluminium. The lithomarsh is a thick horizon of varied colors characterized by the minerals in clays and is bottom portion of that follows the upper crust. Lithomarsh is a compact, massive, and often impure form of kaolin. Then the kaolinite and patches of iron oxyhydroxides make up the bottom part of this laterization. And in accordance with the plasmic zone, there is an impervious layer of saprolite also present in this zone. The study was done on the section of Goa lateritic rock at Merce's quarry by Widdowson in the year 2009. Laterites containing minerals enriched in ferric aluminum oxide makes up majority of Goa's soil. Loamy and alluvial soils are found along the river banks. Laterite, which ranges thickness from 22 to 25 meters, defines 2/3 of Goa. In ultrafarmite, the laterite cover is visible down to a depth of 10 meters due to its high iron oxide content. The soil is very vulnerable to oxidation and leaching from natural causes. As a result, different clay minerals are present in different concentration in these soils. At many locations, the water was also found at very shallow depths. The geotechnical properties. Soil samples were collected from different cities of Goa, and in order to identify trends of the profile and landslide places, a variety of geotechnical tests were conducted. Observation revealed that the reddish-brown lateritic soil is more stronger as they have a lower water content, a greater specific gravity, and a higher unit weight, together with an increased gravel content and maximum dry density. On the other hand, lateritic soils with yellowish or white in color have a lower specific gravity and unit weight. Observation and lesson learned from these landslides were that Goa is predominantly consisting of lateritic soils, and each site provided a different set of data and trend. And the soil profile often altered at even a smaller distance of 5 meters. Lateritic clay-rich soil has been shown to be more prone to failures. A major reason of failures are heavy intensity rainfall and overburden pressure. and because it tends to hold water for an extended period of time and raising the slope's weight and water pressure. At overburden pressure was the result of continuous anthropogenic activities. Numerous landslide and talking about the type of landslide, numerous landslide had a transitional mode of failure while some had a rotational mode of failure, leading to the formation of a dome-like cavity. In most cases, there were no slope stability precautionary measures that were provided along the roadsides. And while the slopes provided with the retaining wall lacked structural stability and thereby failed to withstand the forces due to sudden sliding of the rocks and soil mass. Inadequate drainage system is partly to blame, as the water had no path to flow. Heavy rainfall, excessive infiltration into the soil increased the soil water pressure in the soil, which led to porous structure resulting in shear strength failure. Uncontrolled human activities and natural processes created a weak slip surface and gradients, resulting
you have 1 more minute left. Can you conclude?
Resulted in conditions leading to progressive failure. Goan region of Chorla Ghat, Pilgaon, KRCL, that is the Konkan Railway route, along Margaon and Khandapar are vulnerable to future landslides. Mitigation measures were also suggested, like toe support, retaining walls, and other suitable structures to safeguard the road, cut slopes at the road along the roadways. Another approach was to channelize the surface water into the drains. For smaller heights of retaining, up to heights of 6 meters, cantilever retaining walls were also suggested. But when it comes to higher slopes, higher height of slopes, a multi-step retaining wall or a multi-step gabion wall can also be suggested. Considering the soft saprolite and lithomarge in the lower horizon, a strong toe wall is also recommended. After a careful analysis of the hilly slopes, from the perspective of instability, and permission should be granted for any construction in these vulnerable areas. In order to stop...
I'm sorry to stop you there. Can you go to the conclusions, please? Yeah, your time is up.
The conclusion is that the laterites in Goa are very vulnerable to landslides due to many reasons that I've already mentioned. And then these recent landslides have forced us to pay closer attention and concentrate on the failures underlining causes such as the mineralogy and clay composition of the soil. And bioengineered solutions such as planting vetiver grass can also help in erosion control as well. And research on high-risk areas is crucial for protecting important facilities, and implementing new techniques in slope protection measures is also important. Here are the references, and thank you.
Okay, the floor is open for questions. Any questions? Okay, thank you, Piral.
Thank you.
All right, so the next presentation is by Udaya Raj on application of micropile for slope stability.
Namaste to all. I am Udayraj Neupane from Nepal. I am presenting a small short presentation in 10 minutes, within 10 minutes. I am sharing experience regarding the application of micropiles for protection works for the slope stability as a case study of Japle Khola of Nepal. Basic introduction, Nepal is a very fragile mountain, and rock is very fractured, weathered, just like this here. And previously, Kalpana ma'am also mentioned about the topography of Nepal. This case study is along the Kathmandu, near the very location of the this part is very close to Kathmandu, and the important road to connecting the Kathmandu and other major cities. So the site consists of phyllite rock type is fresh meta sandstones in the slope ground. This is the project site, project area. This part is the Kathmandu Valley, and the road goes through that and turning back to here. And this is the top. This part is the failure area, and during the rainy season, in 2024, the slope was collapsed and the mud was flowed, and the vehicle of the bottom road was buried, and around 40 people died in a single place. Yeah. It's the close view. This is the point. That was 187.5 mm rainfall intensity. Intense rainfall was occurred. This is the photographs. This part is the slide area, and this is the road to the Kathmandu. Yeah, in a single place, 35 people was died. It's the site geology: soft, highly fractured, foliated fine-grained phyllites, metasilt stones, metasandstones, and different layered rock was found. And some land use pattern in previous in this slide we can very much observe. In 2019 there is no any landslide, and land use pattern was not is same. It's the natural one, and then the land was converted to the land planning here, so that water courses of that area is changed here, was changed, so that the landslide occurred. It's the main cause. Yeah, it's the lithology of that area is around 4 to 6 meter thin layer of the soft soil and bedrock existing below that layer. Some minimum testing was occurred. This is the columbium deposits of soft soil. As a result, silty stones, silty soil. Majority of the silty soil is there. Some interventions, both design and construction. During the design, we can make that. It's the mitigation design. Previously, design was done in that way. The micropiles over here. This is the only for supporting piles. This is the dowel bar. It's the old stone masonry wall, and the road sections is the narrow road sections here, and collapse was there, and is the slope almost more than 60 degree slope was here, and it's difficult to widening because it's the very important road, so that solution was design previously. Some photographs of the site is the design one, and previously that part, and the micropiles was done by using pneumatic drilling machines, and this is the PCC layer, and some modifications was done before after during the construction. The micropile also embedded to the same closing towards the main micropiles, shifting towards, and we can see the rock. Here is the bedrock, and the micropiles almost 100% embedded to the bedrock here. It's a 22-meter chain edge here, 22-meter length. Yeah. Here we can see the bedrock, and the micropile was done. Yeah, we can, after the micropiles concreting, we can see these piles. There is no any cavity formations, so that giving the good result. Finally, this was constructed wall. It's a capping wall above the micropiles, and completed before rainy season. Yeah, rainy season, because it was the emergency cases. As very short time have to construct it, so that is the final stage. And there is also this part is another sections. Here is some SDA bar. Also another sections. The design was in different way. Is the SDA rod was drilled. Yeah, some discussions. Is the vertically drilled cement grouted I sections micropiles along with the inclined dowel bars to connect the old stone masonry wall were installed on the valley side slope and got better factor of safety than design time by modifying design drawing during the construction phase, considering site conditions in slope area with minimum space, having minimum where there is no the minimum space, and BG Road 2. Successfully deployment of the micropiles technology in this case supports its border applications for the stabilization in the area of similar mountainous region around the world. Thank you.
Thank you. The floor is open for questions.
So what's the diameter of the micropile?
150 mm.
The section of the I section?
125.
120.
Yeah, 125.
125. 125 I section.
ISMB. Yeah.
ISMB.
Yeah.
Okay, fine. 150. You have put the casing throughout?
No need casing. Yeah.
No casing.
No need casing.
Okay, just at the open hole.
Drilling hole.
Okay.
And inserting the micropiles.
Okay.
And grouting. Yeah.
Thank you, sir.
It's the gravity grouting. Yeah.
Okay. Thank you. Thank you.
Thank you.
Okay, we can take one quick question. And I'm just. If not, I think you're free to go. Okay. Okay. Thank you. So the next presentation is by MPSK Lakshmi on an efficient GUI for risk analysis and of retaining walls using extreme learning machine. Okay, I think yes.
That's okay, that's okay. I think you can, that's okay. Please, please. No issue.
I can use. Okay, I can. Okay. Okay. Fine. Thank you. Okay. Good evening, all. Good evening, all. I am MPSK Lakshmi. I am working in L&T Construction Transportation Infrastructure IC. The title of my presentation is An Efficient GUI for Risk Analysis of Retaining Walls Using Extreme Learning Machine. My co-authors are Mr. Avinash Kumar and Professor CNV Satyanarayan Reddy, sir. I'll start my presentation with the quote. One man's magic is another man's engineering. Super is a null word. With the advent of AI, everything has become possible now. So many number of data sets, everything has become very easy. I will quickly run through the summary of my presentation. In this study, a graphical user interface has been developed to perform the risk analysis of gravity retaining wall and cantilever retaining wall under static and seismic conditions. And Monte Carlo simulation sampling technique was used to automate the reliability analysis using ELM for three different stability conditions, namely overturning, sliding, and bearing capacity failures. So the developed ELM has a very high prediction accuracy. It has been noted that the prediction accuracy was almost 99% in terms of correlation coefficients. And this is developed with different levels of coefficients of variation, enabling users to estimate failure probabilities for different design parameters, including wall height, analysis type, and seismic coefficient. Sorry. So these are the contents of my presentation. And retaining walls are very crucial for transportation infrastructure. They are used in highways, railway bridges, embankments, and at many locations in construction. Classification and functional role. Retaining walls, there are different types of retaining walls: gravity, counterfort, cantilever, and anchored walls. And the key design checks for these walls are especially sliding, overturning, and bearing capacity failures. And settlement is also considered. But in this study, three major stability conditions have been analyzed in this GUI. Sliding, overturning, and bearing failures have been considered for the reliability analysis. So this is the literature review of the reliability analysis done. And I'll just run through the latest reliability analysis, which is done by Mishra et al. And this was developed. This reliability analysis was developed using functional network, genetic programming, and group method data handling for the reliability index estimation. And the latest one, 2023, is by Mustafa et al. Developed probability analysis for gravity retaining wall for bearing failure using deep neural networks, random forest, and extreme gradient boost. So in this present study, the soft computing techniques that were used are artificial neural networks are used, ELM is used, and GMDH models have been done. And Monte Carlo simulation is used for sampling and uncertainty propagation. And 3 stability conditions, overturning, sliding, and bearing capacity have been analyzed. And the GUI is developed for reliability analysis of gravity retaining wall and cantilever retaining wall under static and seismic conditions. And the variability coefficients are also included to assess the reliability sensitivity. So this ELM model has, the GUI has been developed using the ELM model because of very high accuracy. And the methodology has been divided into 3 main stages. And the first part is the deterministic analysis, where we have evaluated the sliding, overturning, and bearing capacities using Excel sheets. And the reliability analysis, we have performed the reliability analysis using FOSM method and Monte Carlo simulations. And soft computing models have been developed using artificial neural networks, ELM, and GMDH for the reliability estimation. And finally, the GUI has been prepared using the ELM model, as ELM has given a higher accuracy. Prediction accuracy out of these 3, and the input parameters are geometrical geometrical values of the retaining wall, cantilever and gravity retaining wall, and geotechnical parameters, namely the C, phi, and bulk unit weight for backfill, as well as the subsoil, and seismic properties have been used. And in the seismic properties, AH value we have introduced, and we have used 5 AH values from 0 to 0.1, ranging 0.02, 0.04, 06, 08, and 1. And output parameters are factors of safety for all these 3 stability conditions, reliability index, and probability of failure. And so as the deterministic analysis is the calculation of these 3 values, stability factors of safety for sliding, overturning, and bearing capacity, the conventional method of calculation using the formulas. And these are the retaining walls considered. Like here we have kept the stem thickness same, and the variable parts are height. Backfill properties we have considered as variable. Here the backfill properties we have considered C as 0, cohesion value as 0 for the backfill soil, and seismic values were also variables here. So this is this is a cantilever retaining wall, and the above one is a gravity retaining wall. And reliability analysis was done using FOSM method, and the reliability index is used calculated using the conventional formulas as per the FOSM method. And the limiting factors of safety for static stability analysis for overturning, sliding, overturning, and bearing capacities are 1.5, 2, and 3 respectively, and for seismic it is 1.1, 1.2, and 2 respectively. The soil parameters mean values considered here are the internal angle of friction is 30 degrees, bulk unit weight is 18, and cohesion is 40. Like for this is for subsoil. Cohesion for subsoil is 40 kilonewton per meter square, and for subsoil internal angle of friction is 20, and bulk unit weight is 19 kilonewton per meter square. So almost 4,05,000 samples have been generated, and 5 different wall heights have been used, 3 to 7 meters. So these are the basic definitions of ANN, ELM, and GMDH models, as these 3 models have been prepared, but for GUI only ELM model has been considered. And this is an overview of the models. And the model performance has been compared with these 3 models, and the R value has come for ELM as 0.98, closely 99%, and RMSE is also less, like 0.23. So ELM has been considered for the GUI reliability indices and probability of failure. Just to show an example, we have given an comparative values for two different COVs and AH values for gravity retaining wall and cantilever retaining wall with AH 0.02 and 0.1 and two COVs like here we have considered COV of 5% for backfill and for angle of internal friction, and bulk unit weight we have considered 4% for backfill as well as subsoil, and for case 2 we have considered COV as 7% and 5%. So what we noticed is when COV is increased, the probability index decreases, and for seismic cases when the seismic AH value increases, the probability index decreases. And for sliding it was more critical, and because based on the subsoil properties also this becomes critical. So this is the developed GUI. So here for backfill soil properties,
you have to conclude, please.
Yeah. This is the cohesion is not considered for backfill. Angle of friction. So here the drop downs are given for analysis where you can consider sliding or overturning or bearing capacity. And again you can calculate the reliability index, probability of failure, and the factors of safety can also be considered here. You can give the seismic AH value, different 5 values we can consider. Height also we can vary here, and there is a drop down for GR wall or cantilever wall. So the limitations are this does not include the stem thickness, base slab thickness, and the subsoil variability is also not considered. So this can be considered for a future development. So the conclusion, coming to the conclusion, so GUI based framework was developed for reliability analysis of gravity retaining wall and cantilever retaining wall under static and seismic conditions. ELM model has been used for the development of this GUI for 3 stability conditions: overturning, sliding and bearing failures. And the framework efficiently estimates reliability index and probability of failure for multiple COV levels. So these are the references, and thank you.
Okay, thank you for the presentation. Any questions? Okay. So Lakshmi, I was just curious, usually when we analyze the seismic slope stability, we use the parameter KH. So you have used AH in your presentation. Is there any specific reason?
With AH, actually, we consider for active earth pressure.
Okay.
I'll go to the previous slides. I'll show you deterministic analysis. We have given those very clear values where we calculate the active earth pressure due to the seismic coefficient. I'll go to that deterministic. I'm sorry. Yes, here actually you can see this is dynamic seismic value of this active earth pressure, and due to surcharge also has been calculated and added for the analysis for moments and sliding.
Okay. Okay, thank you.
Thank you.
So I almost missed him, so we are going to okay, so the next presentation is by Suresh Newpane on comparative assessment of antecedent rainfall threshold for landslide prediction.
Change from this. Change. Okay. Good afternoon. I am Suresh Neupane from Ehime University, Japan. I am going to present here my research topics on comparative assessment of incident rainfall threshold for roadside landslide prediction. These are the content of my presentations. I am going to start with introduction and background. The major national highway and rural roads in Nepal passes through the mid-Himalaya regions. Rainfall-induced shallow landslides are recurring hazard. In every monsoon season, these failures block the roads, disrupt the transportation networks, and causing the significant economic losses and the casualties. The most existing studies have used intensity duration threshold derived from the regional or global data sets such as those proposed by the Kane in 1980 and Gujati et al. In 2007. But these do not reflect the local geological and hydrological and climate variability. In Himalaya, variability of the Himalaya terrain. This region shows the strong variability in rainfall pattern, slope geometry, and the rainfall slope geometry and the soil characteristics, even through the short distance. Therefore, the global thresholds sometimes is not reliable for the specific and this different geological situations. Road widening and fragile geology in the Shivalik zones, which is sedimentary rocks, and the lesser Himalaya, which is the metamorphic rock, is significantly increased. Landslides such as especially during the heavy rainfalls. Sorry. These are the study area. The national Kanti National Roadway of Nepal, connecting capital city to Kathmandu to the southern plain, which is 86 kilometers in length, is vital for the trade and transport, but frequently disturbed by the landslide. Disturbed by the landslide, the road widening and fragile geology in the Shivalik zones is and the lesser Himalaya zones is a major problem in this section. The critical section is 36 kilometers, which is located from the Thingan to Tikabhairab, which is used for this analysis. There are 57 field verified landslide events, which is collected from 2017 to 2024. The rainfall records of 35 years from 1990 to 2040 was collected from the Department of Hydrology and Meteorology, and the inventory was verified by the GPS survey and the satellite imagery. The material and methods. Actually, for the analysis, two main approaches applied to analyze the incident rainfall. One is cumulative incident rainfall method, CAR, which calculates the total rainfall over a fixed number of days, 3, 5, and 10 days, which assumes all the rainfall contributes equally to the slope instability. Uses what that tends to overestimate the influence of the older rainfalls. Another is incident precipitation index, which applies the decay factor for the older rainfalls, where the rainfall API value is given by the K into API T minus 1 into RT, where the RT is the rainfall on the day T, which compares the excuse me. It's not working. I want to, it's not working. Yeah, remove this. I don't want this. It's not working. We use the incident precipitation index in which we consider the decay factor for the better reflection of the natural soil drying and drainage process. The decay factor value of K from the literature, we have found that its value is ranging from 0.8 to 0.98 depending on the soil type and permeability. For this study, soil sample are collected from the study area. And we used to select the suitable value of K after performing some hydrometer analysis and the S map used for the API threshold validation. Soil mesh. Here is some result and discussions. The hydrometer analysis was done to determine the particle size distributions. The soil sample passing from 0.4 to 5 mm sieve. The result of the analysis is presented here. It was found that the soil sample from the upper Shivalik area, this contains the clay fraction, which is 0.005 mm, which varies from 15 to 34%, whereas the silt varies from 21 to 61%, and the sand percentage ranges from 16 to 64%, whereas the sample from the lesser Himalaya zone shows that the percentage of the clay varies from 8 to 15%, and silt varies from 28.2 to 74.6%, whereas the sand percentage ranges from 12.4 to 63.8%. For the API method, the decay factor K was selected from the samples from the hydrometer analysis to reflect the local soil moisture behavior. These are the analysis performed where the daily rainfall on the failure day was compared against the CAR and API values, where 3, 5, and 10 days prior to each landslide and are presented here. This allowed that the evaluation of which method of CAR and API is the best explained observed the landslide event. But we can see here in the CAR method, the most of the landslide were associated with 3-day cumulative rainfalls totals. It assumes all the rainfall contributes equally to the slope instability. It is useful but tends to overestimate the influence of the older rainfall, which does not reflect the real soil drying and drainage process. But in the API methods, which give a much better representation of the slope wetness, we can see here the blue circles, all the landslide events, and the red dot is the landslide event is a special case on 11 August 2019. In this API method, we can see here 3-day and
if you could please conclude the presentation.
Scatter weaker relationships, and the 10-day, we can see here in the 10-day API, all the landslide fall below the 1:1 line, and it confirms that the 10-day API value threshold is 77 mm, and which is critical for the landslide predictions. For the validation,
please conclude the presentation.
Okay, thank you. For the validation, we have used this NASA SMAP L4 root zone soil moisture. In SMAP, the soil moisture, which was lagged by 1 day lag, is corrected by shifting the data forward and aligned with the rainfall peaks and caused by the satellite overpass timing and the model. We can see here that the heavy rainfalls on August 6, which has 70 mm, raised the soil moisture to near the saturation, but when the moderate rainfall takes place in 68 mm in 11 August, triggered the slope failure. This pattern shows that the inverse rainfall moisture trend indicating the instability under the high incident moisture. Then we can conclude that the landslide in the mid-Himalaya are strongly influenced by the cumulative rainfall over 10 days, not just a single day rainfall. The API method with a decay factor provides the more realistic and reliable threshold than the CAR, and integrating the API threshold with SMAP soil moisture create a physically constant data-driven early warning tools. The region-specific thresholds are crucial for the Himalayan region, where the rainfall geology and the soil exhibits a significant variation. Thank you.
Okay, thank you. So any questions? Okay, thank you very much. So the last presentation for this session is by Sushant Rahul on Bayesian updating of slope parameters for specially varying lateritic soil cutting.
Good afternoon, everyone. Mechanics, coupled for deformation analysis, slope stability, probabilistic back analysis, and stability of tunnel in slopes. With my brief introduction, I will start my presentation on the topic that Bayesian updating of slope parameters for especially variable lateritic soil cuttings for Maharashtra. So this will be the flow of my presentation. It will start with introductions, then I will give a brief introduction about the rainfall-induced instability, then the methodology for the probabilistic back analysis, the result, conclusion, and the references. So now we know that the landslide is one of the most common phenomena that is encountered by every part of the world. And it is surprising to know that the 90% of the landslide of the world is encountered in India. From the figure number 1, we can see that the northern part, the northeastern part, and the western ghats of the India are the most prone to landslides. So for the present study, I have selected the western ghats of the India as my study area. And the main reason of this selection of this area is the lateritic slope, lateritic soil, which is very variable in nature. So how the lateritic soil is formed? The lateritic soil is formed by the development of the intense and the prolonged chemical weatherings and underlying parent rocking promoting a warm and humid conditions, which is termed as laterizations. So the Konkan region of the Maharashtra has a very steep lateritic slopes underlined by the basalt rock receiving the around 2000 mm rainfall per year, which makes them very vulnerable in nature, or also very heterogeneous in nature, which makes it very difficult to predict or get the strength parameter of the soil. So what's the solution to this? The solution to get the strength parameter of the slopes using the back is the back analysis of the slope using either by the deterministic approach or either by the probabilistic approach. So what's the gap of study what I have till done? Previously it has done for the isotropic soils, but not for the anisotropic correlations of the remain unexplored. So for the present study, the Bayesian probabilistic back analysis of the MIDC Zarab cutting has been incorporated with the special variability for the cohesion, friction angle, and the unit weight using the anisotropic correlation length using the KL expansions using Optum G2 and MATLAB to obtain the updated parameters and the probabilistic distribution functions. So before starting the presentation, I would like to give the brief introduction what we have done in the previous studies. For the previous studies, we have conducted a site investigation for the Kondavi cutting of Ratnagiri district of Maharashtra, which has failed in the year of 2022. The coupled for deformation analysis was performed on the slopes using the actual rainfall data, and the model was validated with the temporal distribution of factor safety with time, and the factor safety when reaches to 1, it is determined as a failure. After validating this, a similar kind of design chart was prepared for the wide range of cohesion, friction angle, unit weight, and slope angle and the depth of water tables. And this work has been already published in the Engineering Geology. Please refer for the more introduction. Now coming to the methodology of the back analysis, it always start with the site investigation and the collection of soil samples. After collecting the soil samples, the in situ testings and the geotechnical laboratory testing of the soil sample is done for its strength parameters like cohesion, friction angle, and unit weight. After calculating the strength parameters, this strength parameter is used as an input parameter in the numerical model. And now it's time to check whether our determined parameters is okay or not. It is checked by using the predictor and the observed result. Here the results is in the term of factor safety. So we have to check whether our predicted value matches with the observed value or not. Where the observed value is the factor safety that says that is 1, it's the failure. If my numerical model says that the factor safety is 1 with that parameters, then our parameter is okay and good, we can go with it for the mitigation. If no, we have to update our parameters using either by the deterministic approach or by the probabilistic approach. So for the present study, we have used a probabilistic approach as the observed factor safety as 1 and the predicted value as what is given by the numerical model. So now coming to the methodology of probabilistic back analysis. First, the random field is generated, taking the mean of all the calculated parameters and COV and the correlation lengths. Then the sensitivity index for the parameters has been performed to check the sensitivity index of the parameters. Then with that all the means and values, the prior distribution for the parameters is done using for the present study. I have taken the parameters as multivariate normal distributions. Then the likelihood function is defined for the parameters. Then using the Bayesian methods approach, the linear prediction models, the posterior distribution for the parameters has been established. And after solving this equation, the closed form solutions give the posterior mean and the standard deviations for our updated parameters. So now coming to the examples. For this, we have taken the MIDC cutting for the validations, and this was soil. The soil was collected from the slopes, and it was tested in the geotechnical labs, and these are the values which got after the triaxial test, as the effective cohesion as 16 kPa, effective friction angle as 27 degree, and we need to wait as 15.7 kilonewton per meter cube. And with these values, the numerical model was performed, and it gives a factor safety as 1.1, which is not as per our observed value, which should be factor safety should be 1. So hence we have to update our parameters now. So after getting all these parameters, the random field was generated using a mean value of 16 kPa of unit weight of cohesion, 27 degree of friction angle, and 15.7 kilonewton per meter cube as a unit weight. And the COV for all the parameters was taken as 10%, and the correlation length is varied from 1, 5, 10, and 20, where the correlation length for in the depth, it is taken as a 1, and in the x-axis, it is taken 1, 5, 10, and 20. So these are the results after the random field generated for the correlation length of 1, 5, 10, and 20 for the cohesion values. Similarly, for the friction angles, the random field was generated for different correlation lengths. Similarly, for the unit weights. So after generating all the random fields, the mean value of the generated random fields was determined for all the correlation lengths, and we can see that the variation of correlation lengths with the output, it increases with the COV of the parameters increases as our correlation length increases. So now coming for the sensitivity analysis was performed for all the parameters at different correlation lengths of 1, 5, 10, and 20. And these are the results from the sensitivity index. So now coming to the probabilistic analysis, the prior mean, the covariance matrix are formed using μx as the prior mean and the standard deviations, and subscript denotes the material parameters. And it is used as these values. Now, after taking all the input parameters, the posterior means and the covariance matrix is given by the equation is given in this. And we have incorporated all the uncertainties, that is model uncertainties and measurement uncertainties. Now for the examples, the mean value was initially it was 16.05 and 27 degree and 15.7, and covariance matrix is given here. And after updating the parameters, the mean value has decreased for the cohesion, friction angle, and there was increase in the unit weight. So this is the tables showing the results of the cohesion, friction angle, and unit weight of the prior and the posterior for different correlation lengths of 1, 5, 10, and 20. After getting all the parameters, the probabilistic distribution function was plotted for the cohesion, friction, and unit weight at different correlation lengths for cohesion, friction angle at 1, 5, 10, and 20. So now coming to the conclusion part. The study applies a Bayesian probabilistic back analysis to the MIDC ZERAP lateritic soil cutting triggered by the August 2019 rainfall. The random field for the soil parameters like cohesion, friction angle, and unit weight were generated using KL expansion methods in the Optum G2, incorporating the anisotropic correlation length of 1, 5, 10, and 20. Then the output COV of random field increases with the higher CLX and CLY ratio, indicating the greater variability. The sensitivity index reveals that the friction angle has a higher influence on the slope stability parameters, followed by cohesion and the unit weight. The posterior PDF shows that the peak shifted for the lower for the cohesion and the unit and the friction angle, while the higher for the unit weight across all cases. While the peak value of friction angle were narrow, the PDF of the friction angle was narrower than prior, indicating it is a reduced uncertainties, whereas the higher CLX by CLS produced wider PDF. At the last, I would like to say that the Bayesian approach effectively refines the soil parameter estimates by the updating prior distribution based on observed data, underscoring the importance of probabilistic method for the slope failures. These are the references. No, I would like to say thank you for listening me. If you want to connect with me, we can join on LinkedIn and the ResearchGate. Thank you.
Thank you, Sushant. Any questions? Okay, thank you. Thank you for the presentation. So with this, we have come to the end of this session. I would like to thank all the presenters for your very insightful presentation on slope stability and landslides. So we started with the theme lecture by Dr. Surya Sarat Chandra Congress, who presented on the models for landslide susceptibility using remote sensing and deep neural networks. He basically combined the TAPNet and SNAP for the susceptibility mapping, especially in the case of freezing and thawing, which is quite important in Minnesota and US. Then we had a first presentation by Akshat on the fragility of road infrastructure. So the fragility analysis in this case was basically determined in terms of damage factor, where the landslide intensity was given in terms of landslide volume and area, which was a very interesting presentation and help us understand the impact of landslide, where we just don't stop at the value of factor of safety, but we try to understand what the slope's instability can actually cause. There are consequences in terms of the fragility. So thank you very much for that. The next presentation was by Ms. Kalpana on the integrated geophysical and geotechnical assessment of unstable slope. She combined the ERT with the conventional geotechnical testing to assess the stability of slope, and also for a specific case studies, she provided and proposed mitigation measures. So it was localized mitigation measures. Also, then we saw a local landslide from Goa presented by Ms. Priyal. We got to understand the different lessons that we can learn from the lateritic clay slope failures in Goa. The next presentation was on the application of micropile for slope stability for a case in Nepal. The fifth presentation was by Ms. Lakshmi, wherein she presented on GUI, a graphical user interface model for reliability analysis of RE walls for static as well as dynamic conditions. Mr. Suresh presented the next presentation by Mr. Suresh was on the comparative assessment of antecedent rainfall threshold, where he compared CAR, which is the cumulative antecedent rainfall, with the antecedent precipitation index methods for the rainfall threshold development. Finally, we heard from Mr. Sushant on the Bayesian updating of slope parameters for lateritic soil slopes, considering a spatially varying or random field modeling. So thank you all for this time. So with this, I would like to thank my chair of the session.
and also the organizers of the first Geotech Asia for organizing such a session on this important topic of slope stability and landslides. And I have seen that many of the presenters are also from Nepal. Thank you very much for coming here and presenting, for taking your time. We are very happy. Do join us for any of the IGC events, conferences in the future as well. Thank you. So, yeah. With this, I would like to hand over the session to the session coordinator.
Thank you, ma'am. Before we conclude this session, I would like to call upon Professor N.K. Samadia, sir. We would like to present mementos to our chair and co-chair. Sir. Before we close the session, I would like all the participants, chair, co-chair, please join us for a group photograph.